Carmine is a common red dye that is used in foods such as yogurt that is produced by grinding up the beetles of certain scaled insects such as the cochineal. And in addition to second-guessing yourself the next time you go to eat a cup of yogurt, Carmine will also have helped you understand how the number of electron pair domains dictates an atom's hybridization. But before we move on to the content covered in Lesson 2, let's take a look at the Lewis structure for carbonic acid. What you can see is that all of the carbon atoms in carbonic acid have been drawn out for you. But since organic chemistry is the study of carbon-containing compounds, it seems obvious that carbon will be a very prevalent element when dealing with organic structures. And since this is the case, it will be up to you to infer where these carbon atoms are located in a given organic structure. But what you can notice is that for all of the carbon atoms that were initially labeled, we could see that they're located at every vertex of this molecule. So rather than labeling each vertex with a C, it'll be up to you to infer that each vertex is indeed a carbon atom. In the last lesson, we covered certain trends that are present within the periodic table. We learned that as we move down to the left, atomic size increases. So in this case, rubidium would be the largest element we see on this table. And we also learned that as we move up and to the right, an atom's electronegativity increases, so fluorine would be the most stable element on this periodic table, excluding the noble gases, which are very stable structures and we will not be dealing with in this organic chemistry course. Finally, what we also learned from Lesson 1 is that valence electrons are the electrons that are involved in chemical bonding and reactivity, and the group number associated with each element will tell us how many valence electrons each atom has. For example, since carbon and silicon are group 4 elements, each of them will contain 4 valence electrons. Likewise, since nitrogen and phosphorus are group 5 elements, each of these atoms will contain 5 valence electrons. In Part 1 of the Building Blocks Learning module, you were asked to perform several searches within the ChemID database, and what you noticed from your search results is that, generally, for organic molecules, valence electrons are paired. And what we'll learn today is that these valence electrons can come in two types, either as bonding electrons or non-bonding electrons. The non-bonding electrons can also be called lone pairs or unshared pairs and will be represented by 2 dots surrounding a given atom, while a bonding pair of electrons will be represented by a single line between 2 atoms and it represents a single pair of electrons. These bonding and non-bonding valence electrons can arrange themselves into electron-dense regions within a molecule, and these electron-dense regions are known as electron pair domains. There are only 4 types of electron pair domains that we will need to consider: a single non-bonding lone pair, a single bonding pair of electrons represented by a single line and known as a single bond, 2 bonding pairs of electrons which is represented by 2 lines, or 3 bonding pairs of electrons which is represented by 3 lines. It is important to note that even though the multiple bond domains, such as the double bond domain and triple bond domain, contain multiple pairs of bonding electrons, each one of these domains will count as only one electron pair domain because they are located in a single electron-dense region between 2 atoms. The way in which the number of electron pair domains surrounding a particular atom is related to an atom's hybridization is that if we have 4 electron pair domains around a given atom, it will be considered to be sp3 hybridized. If there are 3 electron pair domains around an atom, it will be sp2 hybridized, and finally, if there are 2 electron pair domains around an atom, it will be sp hybridized. In this final example, we will return to carbonic acid, and in what I thought was a funny turn of events, since carbonic acid is made from the ground-up shells of certain beetles, we will also take a look at the incesticide cypermethrin as well. In this problem, you are to take a look at the highlighted atoms in each of these 2 structures, and based on the number of electron pair domains that each atom contains, you are to label each atom's hybridization with the 1 for sp, 2 for sp2, and 3 for sp3. I highly recommend that you pause this video and practice this example on your own now, but otherwise we will do this example together in just a minute. Okay, welcome back. To begin, let's take a look at the 2 oxygen atoms in carbonic acid. The first oxygen atom has 2 non-bonding lone pairs and 2 single bonds, so it has a total of 4 electron pair domains, and since it has 4 electron pair domains, it will be sp3 hybridized, and I will label it with a 3. In this next oxygen atom, we can see that it has 2 non-bonding lone pairs and 1 double bond. So even though the double bond contains 2 pairs of bonding electrons, it only counts as 1 electron pair domain, giving this oxygen a total of 3 electron pair domains and making it sp2 hybridized. Moving on to the cypermethrin example and going from left to right, we could see that this first atom has 1 double bond and 2 single bonds for a total of 3 electron pair domains and is therefore sp2 hybridized. The next atom over has 4 single bonds and 4 electron pair domains and is therefore sp3 hybridized. This third carbon atom has only 2 electron pair domains, a triple bond and a single bond, and is therefore sp hybridized. And finally, this last carbon atom, just like the first atom we took a look at in cypermethrin, has 3 electron pair domains and is sp2 hybridized. With your understanding of electron pair domains and how they determine an atom's hybridization, please proceed to part 2 of the Building Blocks Learning module and pay tribute to the King of Pop.